Today it is my pleasure to speak with Dr. Carl Olander. Carl is an original co-founding member of ATMI, and while now retired, still acts as a consultant in the specific areas of innovation, materials, and material handling systems. For the past 15 years, Carl has had a particular interest in solving what had been very difficult problems in delivery, storage, and handling of potentially toxic and hazardous materials in the semiconductor fabrication process. Carl, thanks for meeting with us today. I'm excited that you're here to be able to speak about SDS, Safe Delivery Systems. Can you tell us a little bit about how SDS came to be?
Thank you very much, Chris. It's really my pleasure to be here today to talk about something that has made a significant impact to the semiconductor industry, certainly been very important to ATMI. And speaking for myself and the few colleagues who are involved in this, presented some pretty unique challenges and opportunities along the way. I guess I would say, SDS was inspired by a need within the industry that ATMI perceived back in the late 80s in talking with environmental health and safety professionals, fire professionals. They were all concerned about the ever-increasing and expanding use of hazardous materials, highly toxic materials in the semiconductor manufacturing process. The particular chemistries, molecules of interest, for the most part, were gases, highly toxic, and pretty much very reactive to boot. So the industry at that time was spending large amounts of money on gas containment, if you will, gas monitoring systems, ventilation systems, emergency release scrubbers, and the like. And pretty much for the next 2 decades would do that as well. So again, we perceived an opportunity for ATMI to make some inroads there and to try to think outside the box a little bit.
So what did you do after it was developed? I mean, what were the next steps for you?
Well, we're looking at a process here historically. It probably spans 20 years. So if I can take you back to the beginning a little bit, after we ascertained there was this need, ATMI did a lot of brainstorming together, and we basically had a culture that said, because we're new, because we're a startup, if we're going to make an impact, let's try to make a big impact. So, we tried to do some things that would clearly redefine how these materials would be stored and used. In our assessment, it really was the fact that these are high pressure materials, most of them, and it's the pressure is really the root cause of gas releases and the potential catastrophes that can evolve from that. If we could eliminate the pressure component from this equation, then while these materials are still pretty toxic, they wouldn't have quite the potential for real accidents to occur. And so we formulated game plans that would remove this pressure component, and we divided that into what I call 2 parallel pathways. I mean, realize we're a small company, only a couple of people working on this, but because we were small, we didn't know we couldn't do it, I guess. So
it's interesting how sometimes we're asked to solve a problem in a very unique way. So when would you say is the right time to start looking at a solution maybe from a different perspective?
It's not a flip answer, but in some respects, the bigger the problem, the more you need to kind of get outside the box and try to really innovate. And that's what we did with the SDS. We wanted to do something that was going to have a significant impact in the industry. And we started really along 2 pathways. We knew we wanted to get rid of pressure. We knew the industry pretty much wanted to keep the same molecules of interest, that is, they didn't want to change chemistries. And so we looked for ways in which we could attack that. And the first the first process we went with was a gas generator. We liked that approach initially because we would start with a precursor of what we wanted and chemically transform that into the molecule that we wanted, and then use that. So inherently inventories would be low. If there was a release or any kind of problem, then the magnitude of that problem would be inherently small. We were successful in getting government contract money to actually build a gas generator for arsine. We built a prototype. We tested it at the University of Southern California and ran it for 6 months. The gas quality was good. The compound semiconductor devices all were good. But at the end of the day, we came to the conclusion that the gas generator approach, while it accomplished a lot of things we want to do, was just too complicated to be a commercial success. Too many moving parts.
Mm-hmm. So in that regard, SDS is a very simple and elegant solution, isn't it?
It is about as simple as an approach you can get to it. And SDS was sort of our plan B in all of this. Through the literature and through our research as we were developing the generator, our backup plan, and I guess when you try high-risk ventures, you should always have multiple backup plans if you're that fortunate. Sure. We thought that this was a possibility, that we could basically immobilize gas molecules within the pore structure of various solids called sorbents. And initially, from a very simplistic chemical view, the gas sort of forms a physical chemical association with the solid, with the walls of the solid, and it basically behaves more like a solid. It's in a more stabilized state. It loses some kinetic energy. The vapor pressure goes way down. So that's really what we're trying to do, is eliminate the pressure and form a stable sort of complex so we could store the materials. Mm-hmm. And we were fortunate there. We won a competitive contract to build kind of an early prototype SDS gas delivery system for the Naval Research Lab down in Washington, D.C. They were using a lot of arsine in their facility. Being that close proximity to Washington, they had a lot of people looking over their shoulder, and they wanted to try to do something a little different. So we won a contract. We got an opportunity to not only build it and develop and gain some experience in developing it, but also to study the fundamentals of the gas-solid reaction, or the conditions under which various sorbents and gases would react and how they would behave, mm-hmm. and gain considerable experience there.
So it sounds like a sort of Velcro for gas molecules. I guess people probably beat a path to your door, huh?
I wish they had beat a path to our door. We still had considerable work to do at that point, Chris. At that juncture, we had pretty much gotten pretty close, but we weren't quite exactly there. We knew that we had the chemistry people wanted. We knew how to store the chemistry in such a way as to remove pressure as an active component in the equation. And we also knew that we could use negative pressure or vacuum, mm-hmm. to withdraw the gas from its, quote, stabilized state. It was when we really focused on ion implant that we thought we had a very technically viable process, if you will, because the implant process is run at very high vacuums, very negative, very low pressures, and so we had lots of motive force to withdraw the gas. And it's interesting, implant was sort of the kind of perfect storm, if you will, of all this coming together, because of the fact that these cylinders actually had to be stored inside the tool, because the tool has a considerable voltage gap to ground, so you just can't pipe this gas in from the outside. It has to be stored physically inside the implanter, and that posed its own set of unique problems. Mm-hmm. So when we got there, we thought we had a system that would interest people. We still had a lot of homework to do. We spent a lot of time with Semitech, with the implant manufacturers, explaining how it was worked, teaching. We spent a lot of time teaching and I guess doing missionary work along the way. We were very fortunate that AT&T in Allentown actually said, hey, you know, if you want to hook one of these things up and try it, we're game if you are. They saw the potential advantage. Jim McManus from our lab went down and hooked up a cylinder on a Friday afternoon. Within a few minutes, we had the beam current, everything was in the sweet spot, and it was working great. And we said, you know, we'll come back next week and we'll play with it some more. Little did we know, or even Dan McKee, who was the fellow who allowed us in the door, that they actually ran product on that tool over the weekend. And so we actually had kind of our acid test early on. Not only did it work right, but it produced acceptable semiconductor components as well. So we were very fortunate in that sense that we got a chance to take it all the way. And then after that, it was a system that would work. We knew that. What really, I think, made it a commercial success or commercially compelling at that point was because of the safety features that SDS afforded, because the threat of a catastrophic release was pretty much off the table at that point. We could do some things that heretofore the industry was reluctant to do, and that's really go from very small cylinders to bigger cylinders, go from using dilute dopants in hydrogen to using 100% material stored on a solid. So we could maybe improve the deliverables from a cylinder maybe 20, 25 times. We could reduce the number of cylinder changeouts by that fold, and through the process, for those implanters using cylinder gas, we increased the machine availability, the throughput, maybe 50%, something like that. It was a dramatic improvement. The other thing in the industry, about half the industry was using solid source vaporizers. Instead of using gas, they didn't want to deal with gases because of this safety issue. They used solid sources that they would heat and vaporize to get the metals off they wanted to implant. That was a very cumbersome process. Going from arsine to phosphine, species to species changes were slow. Took maybe an hour or so. We actually brought those people back to the fold. About half the tools converted back to gas. Gas to gas species changes take maybe 5 minutes. So we brought a lot of people back. We improved machine efficiency dramatically. And we were able to basically, from both a safety and a cost value sense, basically prove the point.
I'm curious, was safety alone enough to ensure commercial adoption?
Actually, Chris, I personally always viewed the safety aspect as more enabling than anything else, because pressure was removed from the equation. We were able to do some really interesting things with larger cylinders, delivering a neat or 100% dopant, and on that basis, improve machine availability dramatically. So I think to be honest with you, we needed both. We needed to be safe, but we had to have some compelling economic reasons to go with it for us to be considered a real success. And we sort of had the perfect storm of all of that. So we had the process, and we had the process economics to make it work.
How have customers typically valued SDS in their operations?
Perhaps the most documentable study I can refer to is one that IBM did with Semitech back in the mid-90s, where they took a very systematic view, look at how the SDS integration would affect their machine availability and product throughput. At the end of the day, they published a report that basically said it was worth on the order of $50 million to them on an annual basis to convert. So it was a very compelling kind of number.
Oh yeah. So how it seems like you basically have jointly worked with your customers to sort of frame up their desired safety improvements and to realize economic benefits?
I don't want to overuse it, but it is kind of a kind of unique situation of being able to provide the customer the chemistries that they want in a form that makes them comfortable to use it, in a process that where it's sort of a drop-in, very transparent. We listened a lot to our customers. We also expanded the product line to include other dopant species that they wanted to have, so we could literally give them an all SDS gas box if that's what they wanted to do, and allow them to take advantage of reduced ventilation and other cost saving measures that come from having pressure really removed from the equation.
Mm-hmm. Carl, can you tell me a little bit about what your experience was like with early SDS customers? How did they help influence the design and the use of SDS?
I think the best memories I have are really of the early adopters, the folks who were willing to take a chance on a new technology because they also had the vision of what it would do for them within their companies and the advantages that it brought. We were fortunate to work very closely with customers as we rolled this out. Worked again very closely with Semitech. We needed a lot of help with the original equipment manufacturer because we were only a small group. Back then there were only 5 of us involved. Luping Wang, Glenn Tom, Jim McManus, and Doug Edwards were the principals involved, and I was lucky enough to kind of be the front man. I got to stand up at meetings and talk about what we were doing and present some of the story, but we really had a very solid, small but solid crew in the background. Mm-hmm. Also Bill Kroll at Matheson. You know, gas companies, when we first brought this to them, by and large, weren't interested. It didn't fit the mold they were used to. Bill Kroll, I guess I call him a bit of a visionary at that time, maybe still a visionary now, but Bill Kroll really had the vision to see what this could do for his company as well, and we needed their help mm-hmm. to really roll this out on a worldwide basis. Mm-hmm.
So where does SDS stand today?
I think it's an unqualified success story. It's a technical success. We overcame a lot of challenges along the way. We had to have our alternatives lined up because it wasn't a straight path to the end zone. It was a rather torturous path in terms of trying to work out all of the surprises that came along the way. But as a technical success, it's a 10, and as a commercial success, it's at least that. So fantastic. I'm thrilled to have been a small part of it over time. So.
Thank you very much, Carl. It's a pleasure to speak with you today. Dr. Carl Olander, original co-founding member of ATMI. Thanks for watching.